All right, on to page 6 of this note packet for chapter 1, sections 2 and 3. This actually begins section 3, measuring segments. So first thing we need to define is a segment. Segment AB, which this is a picture of, is a finite object. It starts at point A and ends at point B, or we could say it starts at point B and ends at point A. You always name segments by their endpoints. So if I were to draw you a picture, what's the name of that segment? Absolutely. You could call it segment CD, or you could call it segment DC. Okay, notice the symbol for a segment is a bar over the two endpoints. You don't put a dot on the end of the bar, even though there is a point at the end of your segment. The next object is a ray. A ray has one endpoint and extends indefinitely in one direction. This is a picture of ray AC. The first letter is always the endpoint. The second letter is just a second point that the ray passes through. The symbol for a ray is an arrow, and it always faces to the right. So, if we were asked to give 3 names for the ray drawn below, and again, I am talking about the entire ray. There are also smaller rays contained by this, but for now, we just mean the large ray. 3 possible names would be ray MO, endpoint, point that it passes through. Ray MP, or ray MY. Okay, all of those would be acceptable names for this ray. Opposite rays, continuing on to the bottom of the page, opposite rays are rays that share the same endpoint and they have to be collinear. If you remember from the previous pages, collinear means on the same line. So pictures of opposite rays would be and I'll use a different color to illustrate the fact that they are separate rays. So in this picture, opposite rays would be ray AM, which would start at A and go through M, and then ray AB. Starts at A, goes through B. Those would be opposite rays. Not opposite rays would be a picture like this. Even though ray BA and ray BC share an endpoint B, these two rays do not form a line. So these would be not opposite rays. Another example of not opposite rays would be if I had a picture like this. And this is everybody's favorite answer that doesn't work. If I said ray BA and ray AB. Okay? Ray BA starts here and extends to the left. Ray AB would start here and extend to the right. Even though the two rays will end up covering the entire line if you stack them on top of each other, they share more than just an endpoint. They also share all these points right here where they're overlapping. So technically they do not qualify as opposite rays. An example of opposite rays in this picture would be ray CB and ray CD. Those would be an example of a pair of opposite rays in that picture. That's one example. There are several others that would qualify, but again, be careful of the overlapping ray, and this is a very common mistake to just switch the letters. Okay, continuing on to page 7. Okay, Okay, on page 7, we start with the definition. Congruent is a word that's used to describe objects that have the same size and shape. The symbol is an equal sign with a tilde on top of it. Notice these two statements. In this statement, we're saying segment DE is congruent to segment FG. Again, we're saying that one object is the same size and shape as another object. Okay? Another rule of thumb for this is the congruent symbol has a little tilde on top of it. So when you're writing these letters, you also need to put a bar on top of the letters. When we use an equal sign, the equal sign doesn't have anything on top of it, and therefore we wouldn't put anything on top of DE or FG. So that's a good way to remember. Now you'll notice the length of a segment is written by just writing the two letters without the bar. And that's very important, okay? Without the bar, we're referring to a number, in particular, the length. With the bar, we're referring to the object itself. Also, be careful because in algebra, when we put two letters together, that meant multiplication. In geometry, it's talking about the length of a segment, so be very careful with that. Okay, more vocab. The coordinate of a point is a number assigned to the point on a number line. And you calculate the distance between points on a number line by taking the absolute value of the difference. And don't forget, difference is the fancy math word for subtract. The difference of the coordinates of the points. Okay, so in this picture, if we take a look, what's the coordinate of E? Good, -4. What's the coordinate of F? Good, it's 9. Okay, so if we take a look at this, again, the coordinate of point A is -9. Coordinate of point D would be 6. So if we wanted to talk about, and again, notice no bar, so this is the length of segment AD. We, again, use the absolute value. So I take the coordinate of A and subtract the coordinate of D, which leads to absolute value of -15, which leads to a value of 15 being the length of segment AD. You could also have done this by taking the coordinate of D and subtracting the coordinate of A and finding the absolute value of that. That would have been the absolute value of -6, or pardon me, +6 minus a -9. That would lead to absolute value of +15, which of course is still 15. That's logical because the length of the segment should not change regardless of where we measure it from. And so again, we use the absolute value so that what could possibly be a negative will always change into a positive. And we know that distances should be positive values. Okay, we're going to continue on to page 8. Okay, on page 8, we have the vocabulary word for midpoint of a segment, or midpoint, as you'll hear me say. It's the point that separates a segment into two congruent segments. It is a single point, the midpoint. Now, in order to show that two segments are congruent, in the picture, by knowing that M is the midpoint of segment AB, then I know segment AM must be congruent to segment MB, or the length of segment AM is equal to the length of segment MB. Either way you express it, it's logical. The way that we mark this in a picture to show that those two segments are equal to each other, those two segments have the same length, is we use tick marks, okay? A single tick mark, that segment is congruent to the other segment or any other segment that's marked with a single tick mark. There could be 2 of these, 3 of these. If they all had single tick marks, they would all be equal to each other. A segment bisector is a segment, a line, a ray, or a plane, so basically almost any object that intersects a segment at its midpoint. In this picture, you can see that plane Z is intersecting and bisecting segment GE. Notice we have the return of the dashed line to show that the segment is passing through the plane. And also notice the tick marks to show that segment GF is congruent to segment FE. Also, because of those marks, I know F is the midpoint of segment GE. Okay, last thing on that page is the segment addition postulate. And you'll notice I will use the abbreviation SAP. And what it says is if I have a point B that's between 2 other points, and by between we mean both the English version of between, but what we're also implying is that B is collinear with A and C. Okay, so we have these points, and this is our situation, and what it means is segment AB, that length, added to the length of segment BC will equal the length of segment AC. I like to look at this as when you have this visual occurring, that 2 little segments added together will equal the big segment. 2 little segments added together will equal the big segment. All right, let's continue on to page 9. Okay, here's page 9, but we're going to actually stop this video here, and we will continue in the next video for page 9 and 10, the examples for all of this measuring segment business. See you then.